Good morning, good afternoon, or good evening, depending on where you are, and welcome to the webinar of Nautel SuperPower AM. I'm Chuck Kelly, and I'm joined today by Wendell Lonergan, Head of Sales. And incidentally, Wendell, how many years have you been with the company now?
Wow.
Trick question, right?
Trick question. 37 years.
37 years, and you started a lot of the AM transmitters that are still working around the world today. You developed and designed.
Indeed, I started in research with the founder of the company, Mr. Koval.
That's awesome. We're glad to have you in the sales team these days. So what we're going to talk about today is we're going to talk about high power medium wave and long wave. Many parts of the world, long wave is a technology that's still in use. We're going to talk about our NXSeries transmitter. And we're going to talk about MDCL, modulation dependent carrier level, and we're going to talk about the AUI functionality and actually take a quick tiptoe through the AUI of a live unit that's down in our test room. Talk a little bit about Nautel commissioning, training, and support. Talk about a little bit about large systems that we've installed or developed around the world, and then we're going to take your questions. So you'll notice on your webinar panel on the right-hand side of your screen that you've got a place to enter questions for the staff, and you are most welcome to enter questions. We will hold on answering them until the very end, and if we don't get a chance to answer all of the questions, we will answer them. They are logged, and we will answer them by email after the webinar is done. So, I want to talk about the NX series, the high-power solid-state transmitter line for medium wave and long wave from Nautel that works from 3 kilowatts all the way up to 2 million watts. We're talking about big iron today, Wendell.
Indeed we are. Indeed we are. So you see the full family on the screen. Now we've taken a little bit of artistic license, obviously, in the bottom of the 2 megawatt section. The largest single unit we do make is a 400 kilowatt, and then we use various types of combining systems above that.
Right. And for comparison's sake, solid-state transmitters from other companies that are combined for higher power have a much lower block size than we have. We have a single transmitter, NX400, that is driven, acts like a 400 kilowatt transmitter. And so that reduces the number of transmitters that have to go into very large transmitters. Okay, so the things that are important about the NX series are the efficiency, up to 90% efficiency. We've seen efficiencies in certain units higher than that, but that 90% is typical. And in the lower power transmitters, it's lower than that. We have adaptive pre-correction built into these transmitters so that we can adjust for, modify the performance of the transmitter to maximize its performance into real loads. We have built-in spectrum analyzers and network analyzers. We've got a 1.8 megahertz digital direct modulation for incredibly high performance, particularly with digital modes. We have our intuitive touchscreen interface and the AUI. These things, for their power, are very compact, and they handle all AM and long wave digital modes, including all the DRM modes and HD radio. So the Nautel NX400 only takes 4.3 square meters. Brand G is nearly 3 times as large. Well, you can see it all there. Brand T, Brand S, and at 90% total efficiency, the Nautel is more efficient than any of them. We talked about dynamic pre-correction. So this is a block diagram. You want to walk us through this a little bit, Wendell?
The transmitter has dynamic pre-correction. So like most pre-correction systems, it takes a sample at the output of the transmitter, feeds back a signal, and then an error signal is created, applied in inverse to the signal going through to give a proper linear transmission sign.
Okay. And one of the things that people ask me is, what is the LUT up there?
Lookup table.
Exactly. That's what I know.
Yeah. So lookup table, it defines the limits, if you will, of the correction that you can apply. So you know, there's X number of steps you can use in any system. which gives you the resolution, and the lookup table is defined over a few years of experimentation to give us the optimal range.
Right. Right. So if we walk this thing through, you can see my cursor on the screen, I believe. So the audio comes in here in the INQ mode, and it's compared against an ideal signal, and it comes out here with the modifications from the LUT, lookup table, and is processed or up-converted from INQ to RF through the local oscillator to the digital analog converter, goes out the transmitter, goes to the antenna. But there's also a sample taken in real time, comes back through an analog to digital converter, again gets mixed down into INQ, and then an error term is created. What is different between what we transmitted and what we expected to transmit through the delay here? And it goes back here, and let's see here. So it goes through the adaptation process, and then the error terms are sent to the lookup table, and the modifications are made. And the things that we modify are the envelope equalization, AM to AM, and AM to PM. And if we click here and go down here, you can see kind of a block diagram. This is of a 400 kilowatt. So there are 160 modules, which are modulator and RF amplifier. Each of them capable of 2.5 kilowatts, and we have 9 phases of modulator drive, and then we have the controller over here. We have the various power supplies, which are redundant. We have a big honking piece of iron, a mains transformer, where everything goes through, and it comes through a phase control rectifier and choke input filter, and these modules run on about 400 volts.
Just a point on there while we talk about this block diagram. Once you get into very big systems above 400 kilowatts in combined systems, that mains transformer, which typically in smaller transmitters would run off a 400, 410 three-phase system, you will now be working off a medium voltage system around the 10 kilovolt level.
Right. Right, and that actually improves our efficiency a bit because of the reduced losses because of copper losses.
That's correct.
Yeah. Okay, and then this is the controller board. You can see up here at the upper right-hand corner that you have XLR connectors for left and right, and INQ and IAES, and we have the processor that's actually controlling everything, and depending on the power level of the transmitter, may also be creating the AUI. Down here is where the exciters plug in, and they are complete DSP exciters. One thing I always love to point out about this card and the exciters and pretty much the rest of the transmitter, there's no adjustments in here. Look at the number of pots or variable capacitors or variable inductors you have to tweak to get the transmitter to work right. There aren't any. And all of the functionality of the transmitter is controlled by the processors in this system, and you have control over it through the AUI from wherever you are. Okay, there's dual AES EBU, analog left and right, and INQ inputs on this. There's an optional GPS card, so you can do this thing in an SFN if you wish. Let's get to the module itself. The module is, as I mentioned, a 2,500 watt module, but I have seen these things on the bench make 12 kilowatts continuous. I mean, just carrier on, CW, as they say, all day long, and that's pretty amazing to watch. And we only use it for 2.5 kilowatts of power. So this left side of this module is the modulator, which is a 3-phase modulator, and the right-hand side is the RF amplifier with the H bridge of transistors, and the RF drive as well as the modulator drive comes in through the connector here at the very end, the RJ45, which is providing that drive to the module. Anything else you'd like to point out on this page?
Yeah, one cool feature about the module is it has an anti-domino effect circuit in there. So at the output of the modulator, which feeds basically the B plus to the RF amplifier, there's a Hall effect current sensor.
Right, up here at the top.
Correct. And if there's a short circuit on one of the RF amplifier FETs, in older designs or other designs, that would guarantee the failure of the modulator that's in front of it.
Mm-hmm.
But this device is so fast that it will actually protect the modulator FETs. And we've tested this the old-fashioned way by taking a screwdriver and shorting it, the output of the modulator, and it actually protects those devices. So it's a very nice little feature.
Speaking of screwdrivers, the one really nice reason you may have one around is that these 200 ampere FETs in the H-bridge at the output of the transmitter or the PA stage are replaceable with just a screwdriver. There's no soldering at all. They're just big honking transistors that you change with a screwdriver. Okay, moving on. So this is the simplified schematic diagram of what we just saw. So we've got the 3 phases of the modulator here, and coming through the modulator filter, which can be quite broad because we're using 9 phases of modulation in this transmitter, and that allows the modulator filter to be very broad. And then that B+ voltage goes across the H bridge, so we have the 4 drive signals here, and the 4 FETs are here, and the output signal is coupled across that output, and that inductor or that transformer right there is actually a toroid with a pipe going through it, basically.
That is correct. Yep, that is correct. So
okay.
The 9 phases, what that allows us to do is leverage the technology in the modulator filter. So the FETs can actually switch at a fairly low frequency, because as you go up in frequency, there's an FCB squared loss in the modulator FET, so that we gain some advantage of, and it allows us to use an effectively a much lower cutoff filter for the modulator filter, and that gives us a very nice rejection to any of the switching artifacts that are there, so it turns into a very manageable, very linear system.
The other thing that I have heard is that since we drive those 4 FETs individually, we can actually make it so that we don't change state. We don't change the drive state when there's voltage across the device, and that reduces the capacitance losses across those FETs.
That's correct.
Which leads to that 98% efficiency of the PA stage.
That's right.
Yeah. Okay. Very good. One other question that some people ask me is, why do you have 200 ampere FETs in that H bridge, in that output stage? And because you can do the math, and 400 volts or even 200 volts of PA voltage, you don't need that much power to get 2.5 kilowatts out of this amplifier. And the answer is that a FET has more losses the warmer it gets. And if a FET is stone cold, it has its highest efficiency. So with running 200 ampere FETs at a much lower value means that we have much lower losses, and again, that contributes to the 8% efficiency.
Correct.
Okay. This is a side view of that modulator. Again, no adjustments, no pots, totally broadbanded, the entire AM band, hot pluggable, heavy gold connectors on both sides. The heat sink is 2.5 times greater than it needs to be. We're using high efficiency silicon carbide modulator diodes, and we have modulator or balanced RS-422 modulator and RF drive that comes in through that RJ45. We have a series combiner, which consists of 2 parallel copper pipes with ferrite cores which couple the RF output. It can handle many times the required power. It is also broadbanded, and the module isolation relay is one of the only 2 types of moving parts in the NX. The other is the fans. So you can see here within this channel here on the right-hand side, that is a copper pipe going through those toroids that couple the power from each PA to the output stage. And in the output network, this is the only frequency-dependent section in the NX series. It consists of 2 T networks with a shunt third harmonic trap. It's a low Q filter which provides minimal amplitude and phase distortion to the RF signal. The adjustment of the NX series from one frequency to another in most powers of the transmitters can be accomplished in just a few hours. and there are kits with frequency-dependent parts available for all medium wave or long wave transmitters. So basically what you do is you change the tap on these coils and change the connector or the capacitors that are loaded in here. And those capacitors are kind of special too. For the people that are listening that have ever cleaned up a mica with tar in it, these aren't those.
No, these are ceramic, and it's not the same as a meltdown of an old mica capacitor. They were pretty nasty.
I've been tarred and feathered from those things before.
And frequency changes on big systems are actually fairly common.
Mm-hmm.
So, you know, it's very, very typical for a antenna for a large system to request all the frequency change components.
Right. Right. Let's talk about, this is my favorite slide, I think, on this whole presentation, because it talks about what happens and how the power is combined from each of these RF amplifiers or modules. And this is actually the copper pipe in the combiner. And then this is the matching network that we talked about. But there's a lot of things that are going on that are interesting when you start thinking like a lightning bolt. So here's a lightning bolt coming down my tower and going to this output. Now, of course, by the tower, I've got my ball gaps and all those kinds of things. But when it comes into the transmitter, I have the things that come in this way. I've got a series resonant high-pass section here. And right there, I have an adjustable carbon ball gap. Now, the carbon ball gap, it can absorb a lot of energy. It has a high joule rating. But it's relatively slow to activate. And so we put it right by the antenna. There's also, by the way, a static drain choke here that's also in the system. But this is a series resonant high-pass section. Now, it's interesting, why a high-pass section? Because the power of a lightning bolt, as I understand it, is in the range of 100 kilohertz, which is below that of the medium wave band. So we put a high pass section to put some attenuation in line or some series impedance in line with the lightning bolt as it tries to travel to our transmitter. So far, so good, Wendell? So far, so good.
That, yeah, that's just right. The output section is actually a little bit of a band pass circuit, but that's fine, and it keeps the lightning from coming back through, and as it develops, as it dissipates through the system, as it comes back through the tritium, very precise spark gap will then fire.
At high speed.
At very high speed. And take the residual power to ground.
Yep. Yep. The other thing that's very interesting is that all of these inductors along here provide a time delay. And there is a forward and reflected directional coupler port right by the output of the transmitter, which would sense any difference in the impedance of the antenna. And we would sense a lightning bolt coming along as an impedance change to begin with. That is fed as RF back into the transmitter, and it has the ability to shut down the drive to each of these RF amplifiers in, what is it, Wendell, what do you know what that time value is?
It was like 2 microseconds.
Yeah, which is actually, as I understand it, faster than the RF energy from the lightning energy propagating through all these inductors could reach this point. So we, in fact, shut off these modules before the lightning can get to the top of the combiner, which is pretty cool. And remember, this part here is simply a copper water pipe going directly to ground. So it has a direct path, and if lightning wants to jump off that and get into the amplifiers, it's doing through a toroid, through a transformer. So you can see here that in this system we've done our very, very best to minimize the possibility, make it as difficult as possible for a lightning bolt to get into the transmitter and cause significant damage. So here's the things we've been talking about. It's 10 microseconds active VSWR shutdown. There's the tritium gap. There's the carbon ball gap. There's the lighting choke. and then some of the filtering that goes on inside the transmitter as well. So there's a lot that we've done in this transmitter to minimize the potential for lightning or transient or AC damage. Cooling, there's 5 hot pluggable trays per 100 kilowatt cabinet, each containing 2 ball bearing fans. And the transmitter will operate with just one of those fans operating. And the typical fan life is over 11 years. Fan operation and speed is monitored by the controller. And in a 100 kilowatt transmitter, only 10 kilowatts of heat is produced, about the same as a typical 10 kilowatt FM transmitter. And air is drawn in through the rear, through a washable metal filter, and exhausted through the top. And I guess the thing that always surprised me about one of these things, you'll sit there and see a 100 kilowatt transmitter operating in front of you, and you put your hand over the top where the air is coming out. And it's hardly noticeable, the difference in temperature from the ambient air temperature in the room. So,
that's correct.
So in fact, here are the cooling requirements for a 400 kilowatt transmitter. And you can see here the amount of waste heat that is created and how much air conditioning is required for the NX400 and for its attendant power transformer. Then there's power supplies. The big power supply handles a broad range of configurations and are fed through large high-efficiency transformer in a separate cabinet. 250-volt three-phase is fed to the transmitter. Do you want to walk us through these photographs here, Wendell? These are the fuses, right, that go to the modules?
Those are the B+ isolation fuses to make sure that there's no, again, no catastrophic failure that works its way back through the system.
Mm-hmm.
Let's see, that's the rectifier assembly. So this is a very large rectifier assembly. We tend to have a lot of respect for the AC power coming in and the fact that its integrity is not as good as we'd like it to be, so we've always over-designed our rectifiers and our transmitters. And these are a single bought-out unit, and we've had extremely high reliability with it, which is fantastic.
Mm-hmm. And that's actually controllable, so we can raise the voltage slowly, like have a soft start because of that rectifier assembly.
Well, not only does it's a phase control supply, so not only does it have a soft start, but it actually operates a bit like a voltage regulator.
Right.
So as the power goes up, the phase on the rectifiers turn back and regulate the B+ for you. So there's a dual benefit there.
And over here we have the low voltage power supplies, which are redundant, and they will operate with just one of them.
That's correct. And below that you see the reservoir capacitors for the low frequency modulation current draw that's inherent with AM transmitters.
And you get the series chokes here, and then the filter caps there as well.
Right.
Okay. We've also done an awful lot of work with digital radio in the medium wave and long wave bands. Whether it's DRM or HD radio, we've pushed the performance limits. I think we're one of the few transmitters that are out there that actually provide for a direct IMQ feed, which provides the best performance. People tell us that the lock on an HD or DRM radio is faster than it is with other brands because we have the direct feed. We're not using mag and phase to interface with the transmitter.
That's correct, and IMQ is really how we do all our correction circuitry as well, so it's it's a far superior way to do it.
Absolutely. And we do all the advanced DRM modes. Now, I'm not saying these are a good idea necessarily, and I'm not saying the receivers out there will handle all these things, but you're protected in terms of your transmitter being able to do it. Here we're actually having an analog AM signal with a DRM signal on the adjacent channel right next to it, and it all works built into the transmitter.
That's correct, and the transmitter's been proven to be so linear that we can, in fact, actually run at transmitter rated power and meet the mast. Now, typically, you would run transmitter at 40% of its rated power. So in this case, we're running 80 kilowatts of DRM average power into a 200 kilowatt transmitter.
Wow.
and easily meeting the mask and very good MER numbers.
Yeah, when you talk about easily meeting the mask, let's just look at this here. That's just crazy. I mean, how far down? These are 20 dB blocks here. So, yeah, it's huge you're talking about. Okay, next page. And we can do all digital HD radio. Some of the tests that have been done in the United States for all digital HD radio have been done with the Nautel transmitters. And let's see, we're a leader in high efficiency AM transmission. So 90% for the 100 kilowatt and above, and 88% for the 50 and 25, somewhat less at the lower power levels. And we're going to talk about this as well. MDCL is included, and up to an additional 30% of savings in electrical costs with no discernible coverage or performance reduction.
That's
and
right.
It's pretty. Go ahead.
I was just going to say it's being widely used in the United States right now, even though the system was developed by the BBC and in Europe for quite some time, but it's been found to be so such a money saver that it's become very commonly used in the United States. Yeah,
and that's because the FCC basically said that carrier shift, the specification for carrier shift doesn't apply if you meant to change the carrier. So that's the thing that was causing a problem with MDCL adoption in the States before. So, and we do provide all the various algorithms, DAM, full DAM, DCC, AMC, all of them are provided in the system. You just select them in the AUI.
The NRSC has also released a paper that speaks to MDCL2, if anybody wants to have a peek at that. It's just another reference point for you.
Energy savings, you can save really hundreds of thousands of dollars if you're running these things on an annual rate. And this is the efficiency and the MDCL, the effect of all of that in the transmitter. You can save up to $400,000 a year at a 15% after 15 cent per kilowatt hour rate, assuming a 400 kilowatt transmitter operating 24/7, 365. So interesting how valuable it is. And then we get to the AUI. If you want to be able to control your transmitter and monitor your transmitter from a distance, the AUI, just like we have for all of the rest of our products, is the way to go. And this allows, you've got modulation monitors, absolute modulation, spectral analysis, real-time impedance analysis displayed on a Smith chart, digital carrier demodulation shown on a constellation chart for HD radio, pre-correction curves, intensive internal monitoring and metering of voltages, currents, drive levels at all levels, including the power modules.
That's correct, and you know we've done all the design so that we'd have superior digital performance, but the offshoot of that is that the analog performance has become so much better as well because of all the linearity changes in the equipment.
Mm-hmm. Mm-hmm. Do you want to talk about the various instruments that are available here, Wendell?
Sure. The spectrum analyzer is, I think pretty well everybody's familiar with that, but it's an instrument-grade spectrum analyzer, and it will, in fact, let you know if you're operating in a legal mode. Make sure that you're not splattering across your neighbors, and it's fantastic in digital operation. EQ frequency response looks at the error signal applied back to the system to correct for errors in the modulator filter. And if you were looking at that up close, you would see the correction curves go way out to 80 kilohertz, well beyond the audio band. But because of the nature of the digital signal, you have to correct that far out to have excellent performance. Mm-hmm. EQ impulse response shows the impulse response to the filter. So there's all kinds of things that happen in a modulator filter. You have group delay errors, you have amplitude errors with frequency. So and these three displays allow you to look at all three. So there's EQ, filter delay, impulse response, and frequency response to give you the most linear system with respect to errors there. AM to AM correction shows amplitude compensation for the magnitude effects. AM to PM, which is basically what used to be referred to as incidental phase modulation.
Which affected AM stereo.
Which affected AM stereo, indeed, which, by the way, is one of the operating modes on these transmitters that's still included.
Built right in.
Built right in. But it's very important that the phase response to the RF drive is very linear, and a correction circuit makes sure it is, and you can look at the curves to see what that correction is. Signal constellation, which is a great thing to look at. In digital mode, you can tell the quality of your signal very quickly when you look at that. Lysogist plot, again, when you're running digital with left and right information, you can see the stereo information that's there, make sure it's as you would expect. The Smith chart. Smith chart is fantastic for a number of reasons, because when you're tuning for digital operation, there's a thing called Hermitian symmetry, which looks at the impedances on the sidebands of the carrier, and you want them to be equal on the plus and minus side. And it also benefits, excuse me, analog operation as well. So regardless of whether you're running digital or analog, the Smith chart is a great tool to give you the best performance. Modulation levels. This gives you left and right modulation, PDM levels, IQ modulation, all kinds of in-depth information there. Audio inputs. You can look at the different audio inputs and see what level they're at. So it's a troubleshooting tool as well to know how far in the system you are with your audio. If there is a problem, you have to troubleshoot.
So let's just switch over and take a look at an NX transmitter operating down in our test lab. This is just a 10 kilowatt, but the AUI looks very much the same. So you can see we're feeding this one with left channel only audio, no right channel. And you can see the Smith chart that we talked about. I can actually take that up to more or less a full screen and zoom in. Now we're going into a dummy load, so we shouldn't expect much change, but you can see here the little red dot in the middle, that's the actual range that we're talking about, and it's a real network analyzer. You can see that the impedance is relative to 50 ohms, so this is just a little over 50 ohms, minus J 0.05, and at a frequency of 9.3 kilohertz away, so it's a very flat dummy load. But you can see how this test equipment would be valuable, especially at a distance. You can see whether your antenna system is still performing the way you'd want it to perform, even when you're not at the transmitter site, and even with regular modulation. You don't have to take the transmitter offline to be able to take a look at that. Here's the spectrum analyzer we were talking about. You can see here we're meeting the mask by a whole bunch. It's a real spectrum analyzer, so we're 6.45 kilohertz above the carrier, and we're down 45 dB at that point. I can go all the way over. This is 1.1 megahertz over on the right-hand side. Sorry, this is 100 kilohertz from left to right, so 50 kilohertz either side. Is that right? Does that make sense? Yep, it's like 75 kilohertz or something either side, each side, and it's 100 dB top to bottom. So there's a ton of things we're monitoring all the time in this transmitter that provide a lot of information. If I were to bring this over here, I can take a look at the all the settings. We don't have time to go through all of this actually, but we will tell you that there's a scheduler built into the system, so you can change power or change audio inputs or whatever on a time of day basis. You can program it for a year in advance. There's an audio player, so just in case you lose your audio, you can play local audio out of the thing. There's an awful lot of things that we've built into this to make it easier for you to use and more reliable as time goes by. So let's go back to the presentation, unless there's something else you wanted to see here, Wendell.
No, that's fantastic.
Okay. Switch back to here and go to the next page. So you want to explain NX presets?
Okay, so...
Hang on 1 second. I got to push on that. There we go. There you go.
There you go. So presets in the transmitter are a setting that defines the operating power and mode for the transmitter and which audio signal is being used at that particular point in time. So it would include things like I'm operating at 400 kilowatts in double sideband mode, or you could be in DRM, you could be in HD radio, you could be in CQAM, AM stereo, whichever. Your audio input could be INQ, it could be left and right. All these features are part of a given preset. And you can have up to 62, which is more than you've ever used, but they're just there because you can. That's the capability of the system. And depending on the nature of the system, a lot of medium wave transmitters go to a lower power in the evening. So your scheduler could change your preset to go from 400 kilowatts to 50 kilowatts for the evening, for instance. And that would just happen automatically.
In some places, it's actually at sunset, and it's stated in your license. So therefore, what this will do is you can set it up so that the month of March, it goes to lower power at this time, but at the month of August, it goes to lower power at a different time, because obviously the days are longer in August in the Northern Hemisphere.
Yeah.
Okay. And they can also activate those same presets through the web server. So you can do this all remotely if you need to. Okay, let's talk a little bit about the digital modulation. We talked about this a little bit, but we use 9-phase modulation, which means that we end up with a much broader band for the digital performance and a cleaner signal for the analog performance. But it is a digital modulation technique. Yep.
Yeah. So in the one-phase modulator, which is really what HFAT works at, so you can see that it's running at a very low frequency. We're taking advantage of the fact that we don't have to worry about the losses of the effect as you turn the frequency up higher, and because we're switching all the FETs in different phases, the effect of the signal looks like on the 9-phase modulation signal below. So we can leverage that in a modulator filter and come up with a very, very linear system.
This is indeed a very advanced digital modulation technique at the end of the day.
Oh, is it ever?
Yep. Okay. And you can see the proof of the pudding. If you've ever looked at a PDM transmitter and seen the PWM nipple, you can see that there is none because of that AM to AM correction, and there's no visible distortion in the trough at all. That's an amazing photograph.
Absolutely.
Okay, let's talk about how we scale these things up. I noticed I peeked ahead, and we already had a question about how do we combine these 400 kilowatt transmitters? What's the process of it?
Right. So up to an 800 kilowatt combiner, we would use a binary combiner. Mm-hmm. So in other words, two inputs. And so it's a 3 dB combiner, fairly typical in the industry. If you lose one complete transmitter, you would put 1/4 of the remaining transmitter into the antenna and 1/4 into a reject load. And because we don't want to waste power into a reject load, we will then switch the dead transmitter into a dummy load and put all the remaining power of the working transmitter into the antenna. So you're only down 3 dB.
So you've lost, yeah, exactly. Okay.
When you get higher than that, we have a very unique system that actually will take N transmitters. Let's just talk about a 2 megawatt system, just because that's of particular relevance to us these days. Mm-hmm. That would be comprised of 5 400 kilowatt transmitters, and any one of those transmitters can be switched into a 400 kilowatt dummy load for servicing, or in the event that something happens to one of them. And the remaining transmitters then go through an impedance matching circuit, and then get put back into the antenna. So very versatile system, allowing you to operate 2 megawatts and not have any issues with load variation as your inputs change.
Right. Right. And this is what a simple binary combiner we call the NXC looks like.
Yes, and you can see this has an AUI, the same as the transmitters, which has a very nice flow diagram on the front to let everybody know which transmitter, if not both, is operating into the antenna system. And again, this can also be reviewed from any browser in the world that you allow to come in with the proper passwords to see this.
And controlled.
And controlled, absolutely.
And it can do cool things like send you emails or SMSs. Yep,
and there's all kinds of safety features included in this that look at the dummy load, and there's delays. So typically these are very large dummy loads with big fans and louvers, and the circuitry in here makes sure that the louvers are open, the fans are running before it dumps power into the test load. So a very well thought out system.
Yeah, and this is, we're not using, other companies, some of them use third-party combiners. We've designed our own right from the beginning, right down to the switches and the coils.
That's correct, yes.
Yeah. Okay, let's talk about some systems. So this is a high-power combined installation. Looks like 2 300s combined.
That's correct. This is actually one of several systems like this we have installed in the Middle East. And they're operating, fully functional, very happy with them. So these are 2 NX 300 kilowatt combiners into our 800 kilowatt, transmitters into our 800 kilowatt combiner. In this context, we would be medium power combiners, but we have 2 flavors. For binary combining, that's an 800 kilowatt combiner and a 200 kilowatt combiner. And then once you get into the multiple unit combining scenarios, they're custom built and they go right up to 2 megawatts.
Right. Let's talk about that kind of stuff. Do you need me to go back?
No, that's fine. I was just going to make one comment about that previous system actually used we make our own dummy loads as well.
That's right. Yeah, okay.
Yeah. So that's a complete Nautel system we were looking at.
Okay. This is a long wave system.
Correct. You can speak to this one.
Yeah, so this is 4 400 kilowatt transmitters that we've designed into a 1.5 megawatt long wave system. Again, the transmitters are very much the same as they would be for medium wave. There's 4 400 kilowatts, and then the 4-way combiner is right here in the center. So the NXC custom 4-way combiner is there. And then this is a hypothetical 2 megawatt system.
Yeah. With some cement hardening around it every day. So this is fantastic. This is 5 400 kilowatt transmitters, and you can see each one of them with an RF feed into the 2 megawatt combiner. And inside there is all combining circuitry and relays to allow bypassing of circuitry and allow you to do maintenance work in any one transmitter into a dummy load.
Very good. And there's a little bit more information about the long wave. The band works from 129 to 283.5 kilohertz. Again, 90% efficiency, and the other features are similar to our medium wave transmitters. The one difference, I think, is that the filtering process might be a little bit larger. We may actually have a higher box in some configurations. Taller box, I should say.
That's correct, yes.
Okay. And some photographs of systems we've installed. Do you want to talk about these at all, W?
Well, this is our first 300 kilowatt system, actually. This particular customer bought 3 identical units, and this is one of their installations where they've happily installed the transmitters, and let's see, this is 8-9 years ago already.
Yeah, exactly.
Yeah, and so these are operating the same as they did when they were put in. They're very happy with them.
Another one?
Another one of the same customer.
Mm-hmm. Mm-hmm. And let's see here. This looks like some 100 kilowatts. And then there's an old AmpFet down here, isn't there?
This is Brooklands Park. This is a very, very fascinating site in the UK.
A famous site.
It is absolutely famous. It has its own Wikipedia page and all kinds of YouTubes around it. Very, very prestigious customers as far as we're concerned, and we just love supplying our best equipment to them.
Absolutely. And this is another location where we've got some 300s that are on different frequencies and operating and have been now for several years. Another installation. This is a combined system in the Middle East, I believe, that puts out about what, 500 or 600 kilowatts up to.
That's correct. Yeah. There's a couple of identical systems to this.
Yeah, there's the NXC with the AUI in the middle here, all lit up and looking pretty.
Absolutely.
And so to summarize, we're almost on time. The NX series is the most advanced medium wave and long wave transmitter series available today. It's available from 3 kilowatt to 2 megawatts with unparalleled efficiency. It's ready for all forms of digital radio. It's complete with powerful test equipment and Nautel's continuous improvement. I think we just recently added some features to some of these transmitters that hadn't been thought of before, and the customers that have had transmitters for up to 8 or 9 years are getting the benefits of those things. And probably the best thing of all is it's all supported by Nautel's customer service team with our offices in Bangor and Halifax and parts depots, including 24/7 live support by phone, live chat during business hours, and we've never discontinued support on any product. And our warranty on these things is 4 years. And there's places here to get a lot more information. The Nautel Waves newsletter, our webinars are all available online, and this particular webinar will be available online for you to view within the next couple of days. We also have our YouTube page. And last but not least, you can contact me by email at this email address or use the catch-all for sales@nautel.com. And our 47 years of existence and our people in both the Halifax on the left and Bangor on the right factories do very much appreciate you being here today and being with us. Wendell, anything else you'd like to add?
Just thank you for your support, and that's it. Thank you.
Hopefully we answered all your questions. So for Wendell Lonergan, I'm Chuck Kelly, thanking you so much for being with us today. Bye-bye.